All right, so here we are, still talking about the Bohr model of the atom, and I want you to remember these three input assumptions that Bohr brought. This is one of those situations where we've got this stuff, and then a lot of math happens, a lot of recreational algebra goes on, and then there's some results. That's simple, right? I kind of did this back when we did the kinematics formula. Remember the kinematics formulas way back months ago? Remember that? I did the same kind of thing. We had our definitions of displacement, velocity, and acceleration, and then I sort of waved the magic wand and the kinematics formulas popped out the other side. Going to do the same thing here. Not going to do all the algebra. It would really take 3 or 4 videos to do that. I am going to quote you the results. And the results have a lot of symbols floating around in them, but I'm going to simplify them. So it's going to get really messy for a second. Even the results are going to get really messy, but then I'm going to strip them down and make them real simple for you. Okay? So, here we go. The main thing I want you to take away from this is, when we talk about big things, like a rock, or a baseball, or a car going down the street, we don't really limit, say for example, the speeds the car can have. I mean, yeah, it can only go maybe up to 100 miles per hour before it falls apart, in my car's case. But I can really pick any speed between 0 and 100, right? I mean, really. I can, in principle, pick any speed I want to. But with little things, with quantum things, that's not true. It turns out that this electron going around in the orbit can only have certain speeds, and those orbits can only be certain sizes. They are quantized. That's what the word quantum really means. Okay? It means you can't have any value you want. It's like you can't have 42.78 cents. You can have 42 or 43, but you can't have anything in between them. That's kind of the same, but instead of money, we're talking about energy, and we're talking about sizes of atoms, sizes of orbits. Okay? So this electron can't have any speed it wants. It can't have any energy it wants. The atom can't be any size it wants. It can only be certain sizes. And there's one more thing. The wavelengths, of course, that are emitted can only have certain values, which is what started down this whole thing. So the first result, okay, 3 results, has to do with the size of the orbit. Only certain values are allowed. R sub n equals, and this is where it gets a little messy, h bar squared over m sub e k sub e times e squared. And please, if you're taking notes, don't worry about writing these down. Just watch. All that times n squared. That's a lot of symbols, but you see that they came out of the assumptions, right? K sub e is up there, E is up there, M sub e is up there, H bar is up there. This all came straight out of the assumptions. This value here is known as the Bohr radius. It is equal to, it's given the symbol A naught. Is this showing up? Yes. I might use a different color, but yes. A naught is equal to, let me get get it just right here, 0.0529 nanometers. So we can rewrite this result as R sub n equals A naught times n squared. That's the first result. That's the first, our 3 inputs. This is our first output, our first result. The radii of a hydrogen atom can only take on certain values. When n equals 1, radius is A naught. When n equals 2, it's 4A naught. When n equals 3, it's 9a naught. You can't have a hydrogen atom of size 7a naught or 6a naught. It can be 1a naught or 4 or 9 or 25. Only certain sizes are allowed. A hydrogen atom can only be certain sizes. It can't be small or big. Variably, continuously. It can't be whatever size it wants. There's only certain sizes, R1, R2, R3, and R4, etc. That's all it's available to it. That's it. Okay, the second one has to do with energy. With each one of these different orbit sizes is associated an energy. So E sub n is equal to minus me k sub e squared, I think, yes, e to the fourth over 2 h bar squared times 1 over n squared. This big, in the same way that this big mess of constants here, we compactified it down into a naught. We can compactify this down. This combination of constants gives us 13.6 electron volts. That's a unit of energy. I think we said this before, but I'll say it again. 1 electron volt is 1.602 times 10 to the negative 19th joules. That's showing up weekly, but it's there. 1 electron volt is defined by that much. It's simply a unit of energy which works on atomic scales. Okay, it's like using light years. When we're talking about stars, it makes more sense to use light years than meters. It makes more sense to use electron volts, EVs, when we're talking about atomic energies, because they're small. For a single atom, the energies are quite small. So we use electron volts. So we can write the second result, E sub n is minus 13.6 electron volts divided by n squared. So if this is the first big result, this is the second big result. That's the second. Okay. And I'll hold on to the third for the next video. We'll do the third, and then we're going to summarize them all together. Okay? And again, and I'll say this again, believe me, I'll say it again. But the point of this is that the energy of the atom can only be certain values. It can't be any value you want. The speed of my car can be any value I want between 0 and 100 miles per hour. In principle, I could get it going 42.77898088 miles per hour. But this would be kind of like, this equation here is kind of like if I can make my car go 0 miles per hour, 5 miles per hour, 15 miles per hour, 25 miles per hour, but no speed in between. Only certain energies are available to the atom. Okay? There's not a continuous range of energies available like it is to my car. When things get small, only certain values of very important quantities are allowed. Okay? That's it. That's the real qualitative thing I want you to take away from this. It's just like as if my car could only go 5 or 15 or 25 or 35 miles per hour. And it could jump from one to the other. I could take it from 15 and instantaneously push it up to 25. But it wouldn't go through 20 on the way there. It'd be 15, and then all of a sudden, boom, it'd be 25. And then I could stop it. I could stop it, and as I went from 25 to 0, I might go down through 15 and 5, or I might go straight to 0. It's like it can be any one of those in any order, but it can't be anything between them ever. That's what's happening with the atom, and that's what I want you to think about. It's a weird world, okay? We'll come back to result number 3, and then I'll summarize them, And then we'll start talking in the last lecture probably just about how to sort of visualize this a little bit with the hydrogen atom. All right? See you then.